Hi there, my name is Emanuel Gollob, and today I'm going to be talking about using robotics and artificial intelligence to physically explore a space of aesthetic possibilities. This is joint work with Magdalena and Johannes Braumann, and we together did it at the Creative Robotics Research Lab at the University of Art and Design in Linz. So let's get started. Imagine two people walking into an exhibition and looking at the same sculpture. Even if context, sculpture and time are the same, I guess both will very likely develop a very different aesthetic judgment as well as aesthetic emotion. Empirical aesthetics research has made a huge process in mapping all these components involved in this process. But what if we just tackle the problem from the other way around and think about a sculpture which is reacting on the aesthetic emotion, or maybe even targeting a very specific neuronal outcome? With our explorative research, we are building on a model of aesthetic perception. We are using generative adversarial networks. We are trying to implement a concept of an interaction concept of an affect loop, and we are combining it with parametric robotic control. Each of our artifacts, and there are three, and I'm going to present them to you very soon. Each of them is consisting of an EEG device, a KUKA robotics arm, a generative adversarial network, as well as a database. So now let's get to the first device. For public interactive setups, we are using a Muse EEG headband. It has 4 electrodes, it's like a consumer headband. For more advanced settings, we are using an Enovio 8 EEG cap with 8 electrodes. On my right side, you can see the electrode positions we are using. Also in our paper, you can find more details about how we process our EEG data. So let's continue and move forward to our adapted Gan setup. For our adapted Gan setup, we are using a deep convolutional generative adversarial network combined with a physical execution. So the Gan is continuously running in the background, and sequentially we're taking out samples and executing them in the physical space. Whenever we are executing a sample in the physical space, we are using a robot execution, and we start to measure the EEG feedback. Once the EEG feedback reaches a certain threshold defined by the targeted EEG feedback we defined in the beginning, we are gonna save the sample into our database. Later on, the discriminator is trained on this database and is again training the generator. As our aesthetic in the flux demands a near real-time machinic reaction, we are using a KUKA KR6 R900 robot. It has 6 axes and a maximum reach of 900 millimeters. We control it through the real-time control software MX Automation and the Grasshopper plugin KUKA BRC. Each of our choreographies is defined in a parametric logic. So there are 256 mutable parameters in a range from 0 to 255, and that also makes them translatable to a 16 by 16 grayscale image. Over the last year, we created 3 artifacts within this work, each of the artifacts providing different levels of interactivity. So first, I want to show you doing nothing with AI 1.0. It's targeting default mode network, as several researchers found correlation between default mode network activity and aesthetic perception, but also it's in line with our conceptual interest in doing nothing activity. Here you see doing nothing with AI 1.0. Whenever the receiver is putting on the EEG headband, the generator generates the first sample and the robot starts to execute the sample. From that point on, we are collecting EEG data and interpreting the data compared to our defined targeted EEG goal. Once a certain threshold is achieved, the sample is labeled, and either we just mutate it slightly because the labeling was positive, or if the labeling was negative, the generator is going to produce a new sample. Our second artifact is Doing Nothing with AI 2.0. It builds on Doing Nothing, our experience from Doing Nothing with AI 1.0. And in the first iteration, we found out that viewers untrained to movement nuances had a hard time to recognize small changes, small parameter changes. So we extended the space of aesthetic possibilities with a parametric soundscape as well as a parametric visualscape. Here you can see a video of the experience, and as you can see, we also tried to eliminate the context factor and create an immersive experience. Additionally, we let the perceiver walk freely in the space. The next artifact we're going to present today is Violin Improvisation and Doing Nothing with AI 1.0. In this iteration we were working with a professional violin player, and he was improvising a violin play based on his perception while being connected with Doing Nothing with AI 1.0. Someone preferring to define what arrives at the perceiver side could take the step of defining an aesthetic rather in a relative way than in a strictly defined way. Throughout our work, in all artifacts, we did not save any EEG data. We only saved choreography data. And as several components were not standardized, we clearly distance ourselves from interpreting those data, but we only want to share our observations and experiences. The outcome of our work we present here is not an optimized aesthetic, but more an embedded interaction. So there are two or both interactions are acting, learning, and reacting on each other. In our work, we also realized the positive impact of targeting unconscious brain network. It was very beneficial for the interaction quality. And we also realized that it was a negative impact to have technological layers visible, like for example, security devices or EEG devices. Looking at future research, we would be very interested to also trying to target different EEG feedback. And as we mainly presented and set up our artifacts in an art and tech bubble, we would be interested to also try it with a more diverse sample. For our work, it was very beneficial to use a Gan setup as it was very much straightforward, but it would be also very interesting to try explainable learning systems and have a look on how the learning process is happening in the back. Part of our motivation was to research how brain activities are changing in parallel to digitalization. So it would be also very interesting to do this explorative study in a long-term perspective. All of this couldn't have happened without a huge team, so we are very thankful to everyone mentioned on this page. And it was only doable because several institutions supported us. Thanks for that, and I'm looking forward to our discussion.